class of evidence that provides a way for judging if the universe is the result of a fluke or some impersonal process or the result of purpose or design.
In the summer of 1999, Gonzalez and Richards initiated a program of joint research. They began their study by considering a characteristic of solar eclipses little known outside the scientific community. These striking events are not only compelling to observe, they also open a portal onto the physics and chemistry of the entire universe.
Really, you can think of eclipses as a giant natural experiment set up that allows us to observe a part of the sun that's critical towards understanding how its light is produced in its atmosphere.
The fact that the Earth is going around the sun and the moon is around the Earth, and the sizes and the distances between the Earth and the moon and the sun are just so to give you a perfect solar eclipse is a wondrous thing, because it allows us to measure the constituents of the upper layers of the sun's atmosphere.
During a solar eclipse, the moon fits so perfectly over the sun that it shields its blinding light, providing astronomers with a view of the star's atmosphere otherwise impossible to experience. At the moment of totality, the pinkish arc of the chromosphere, the atmosphere's innermost layer, becomes visible, and with it a rainbow-like band called the flash spectrum appears when the sun is viewed through a prism. The eclipse of 1870 led to an understanding of the structure of the sun's chromosphere and the discovery of helium, the second most abundant element in the universe.
The spectrum is probably the single greatest source of information about a star. And it was during a couple of historic eclipses in the 19th century that astronomers figure out how the spectrum of the sun is produced. And they only were able to figure it out because of the particular circumstances during a total eclipse.
These circumstances are both precise and crucial. If our moon was slightly larger, it would partially block our view of the chromosphere and diminish its spectral light. A smaller moon would allow too much light from the sun, destroying our view of the solar atmosphere and the flash spectrum.
And so you have to have a nearly perfect match between the sun and the moon, so you don't hide the chromosphere. And that insight afforded by eclipses in the 19th century is what finally permitted astronomers to figure out how the spectra of distant stars are produced. Really, that opened up stellar astrophysics and allowed us to understand how other stars work, because distant stars, after all, are other suns.
The relationship between eclipses and scientific discovery was also revealed in the spring of 1919. On May the 29th, research teams headed by British astronomer Arthur Eddington photographed the sun and adjacent stars in the Hyades star cluster during the darkness of totality. Later analysis of the pictures verified that the sun's gravity bent light from distant stars traveling toward the Earth at the angle Albert Einstein had predicted. Einstein's theory of relativity, an idea that revolutionized our understanding of the universe, had been confirmed during a total solar eclipse.
And that experiment was only possible because the stars become visible during a total eclipse. They're very important in the history of science. And the best place in the entire solar system to view solar eclipses is from the surface of the Earth. I've actually calculated the circumstances for eclipses from all the other planets and all the other moons, about 65 of them, the major moons. And it's an amazing coincidence. The one place that has observers is the one place that has the best eclipses.
Within the gossamer light of a solar eclipse, Gonzalez and Richards recognized a fascinating connection between the factors necessary for complex life and scientific observation. But was this merely an isolated fluke of nature, or a glimpse at a principle and a purpose fundamental to the universe as a whole?
That was the million-dollar question that we continually had before us. What if those things that make a planet habitable also make that planet the best place for making scientific discoveries? That is, what if those rare locations in the universe that are compatible with observers like ourselves are also the best places overall for making observations?
For 3 years, Richards and Gonzalez meticulously tested their idea against evidence gathered from a wide range of scientific disciplines. In the 2004 book, The Privileged Planet, they published their hypothesis. The same narrow circumstances that allow us to exist also provide us with the best overall setting for making scientific discoveries.
In the book, we detail more than a dozen examples of this correlation between life and discovery. And these aren't quirky, marginal examples. Each treats a condition critical to its respective scientific field. Some deal with remote things, like the nature of galaxies. Others are much closer to home.
While a perfect solar eclipse was the catalyst for Gonzalez and Richards' hypothesis, their observations would never have been possible without another, more familiar example of the correlation between life and discovery: the atmosphere of the Earth.
It's striking when you see pictures of the Earth from the Apollo missions or other spacecraft, and you see this very thin layer of the atmosphere surrounding the Earth that sustains all the life that we know on Earth. And so you need a certain mix of elements to support a complex biosphere like ours. Not just any atmosphere will do.
Our appreciation of the Earth's atmosphere has increased significantly during the last 40 years as exploratory spacecraft have probed the solar system. These missions have confirmed that within the Sun's family of more than 70 planets and moons, the Earth is one of 7 bodies enveloped by a thick canopy of gas. Yet among these 7, only the Earth's atmosphere can sustain complex life. And only the Earth's atmosphere is transparent.
It's an atmosphere that's made up of mostly oxygen and nitrogen with very little carbon dioxide and very little other carbon compounds or atoms in the atmosphere that gives you a transparent atmosphere. If we had too much carbon in the atmosphere, we get hazes, organic hazes in the atmosphere, like you see on the large moon Titan, for example.
The dense shroud of gas that blankets Saturn's largest moon resembles the atmospheres surrounding Neptune, Uranus, Saturn, Jupiter, and the greenhouse cauldron of Venus. None of these alien worlds know the stars, or even offers a clear view of the sun.
Now, of course, if you were suddenly transported to Titan or Venus or to one of the outlying gas giant planets, the lack of a clear view of the universe wouldn't be much of an issue because you'd be dead. But that's precisely the point. If we're right, if the conditions for habitability and scientific discovery appear in the same places, then you're going to get conditions like you do on Earth, an atmosphere that sustains complex life like ourselves and also enables scientific discovery of the universe around us.
The virtues of such an atmosphere are continually tested. As the Earth moves through space, it is bombarded by radiation from throughout the universe. This radiation is emitted by the Sun and other celestial objects, including supernovas and distant galaxies. It reaches our planet in wavelengths described as gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio. Together, they comprise the electromagnetic spectrum. Almost all of these wavelengths are invisible to the eye and either lethal or useless to organic life. Yet within this spectrum of frequencies, a thin sliver of radiation proves essential to plants, animals, and human beings.
In other words, there's really just a very narrow part of the electromagnetic spectrum that's going to be useful for living processes like photosynthesis. It's not as if life could have evolved to use gamma radiation or X-ray radiation or something like that. There's really just a narrow part of the spectrum that would be useful to life processes. Well, as it turns out, that's also the same narrow part of the spectrum that is the most informative about the various structures that we discover in the universe around us.
These specific frequencies that enable plants to manufacture food and astronomers to observe the cosmos represent less than 1/trillionth of a trillionth of the universe's range of natural electromagnetic emissions. Fortunately, it is the type of light our sun produces in abundance, and that most easily penetrates the filtering shield of our atmosphere